this database is we can look at technologies, emissions, and impacts associated with all those things. So if you think back to what you've been doing in 411 and in the early parts of 412, we've been breaking these things out into these kind of different baskets of different processes or technologies, their emissions, and then impacts that are related to those particular emissions. So there are lots of ways that we might do that. So we can identify certain emission categories or classifications, and we can do that as in that example, we have specific units for most of these emissions. Many times it'll be kilograms or milligrams, and we have a concentration unit per meter cubed, but generally we'll have some mass basis, and those we can apply to air pollutants, water pollutants, things that get trapped within the soil. So we have a wide variety of things we can apply those to. But those emissions don't really give us the sustainability impact criteria. So we want to go from emissions to an impact, to something that's related to an impact. So in order to do that, we often need to define what is that impact we're concerned with, and what are the particular emissions, and how do they relate to that impact. So this is one example of the global warming potential where we can take specific emissions, specific airborne emissions, so it might be carbon dioxide, very common, methane, chlorofluorocarbons, other things that have a particular global warming potential. So we have our database where we get a mass of emissions. That doesn't give us this impact. So in order to go on impact, we have to come up with some sort of equalization term between kilograms of something emitted and this potential impact that we have. So for the global warming potential, we often go back to, well, their impact for a certain chemical over here is going to be related to this concept of radiative forcing. Does anybody remember from chapter 6 last semester what radiative forcing means? It's an analogy to that. Energy density, that might be pretty good, but what in particular about that energy density?
It seems like pressure.
Somewhat. Pressure on what?
Well, it's like an analogy to water.
So we have pressure. This is a pressure, making that analogy. What would the pressure be upon? So what specifically in the environment? Because the environment's a big descriptive bucket. Can we get more specific than that? Anybody else can jump in. I'll pick on Alex. So what do you have in your drink container?
Coffee.
Coffee? Why is it in that container?
So it can be held.
So it can be held? Why not in a solo cup? You can have a lid? Well, you said so it can be held, but what about makes it be held? Is it compared to like a solo cup if you just put it in thin plastic?
It's insulated.
It's lid, anything else? Just lid?
It's insulated.
Oh, insulated. Thank you. I misunderstood that. So that's the right answer, by the way. So the insulation provides a thermal barrier, right? Doing something hot and cold. If we weren't insulated on the surface of the planet, we were at the same temperature of outer space, we'd be pretty cold, right? So we need some sort of insulation areas, some sort of thermal barrier between where we live down here on the surface of the planet and outer space. Our atmosphere provides that insulation. Our atmosphere is made up of a mixture of a bunch of gases, right? So instead of, in Alex's case, it's that metal container, probably double wall, metal with air in between, actually. So even in this case, air provides some insulation. That makes sense? So in the same characteristics, the atmosphere is an insulator for our planet. And depending upon the materials, if we have a paper cup or a metal insulated container, the materials have different insulation properties. Make sense? What this says is that each of these greenhouse gases, each of those individual materials is going to have a different insulating property. That's pretty down to the fundamental basics of thermodynamics and the chemical structure of the molecules, right? Those things just are. They're not really open to debate. So because of that, they're going to have a different insulation parameter, and as we change the insulation capacity of our atmosphere, that insulation barrier, based on the concentration of these chemicals in the atmosphere, we change what we call, we're just going to give this a name now for this insulation potential, the radiative forcing, or the global warming potential of each of those components in the atmosphere. Does that make sense to everyone? So radiative forcing is just really the insulation potential of that particular compound based on that particular chemical structure in the atmosphere. Now, when we go through all this analysis, there's a table in chapter 6, and I'll just reference it now, but if you go through all the analysis of all the different gases in the atmosphere, all the different radiative forcings, the things that make the surface of the Earth warmer and the things that make it colder, you add those all up, and they come up very closely to equaling the amount of the effect of carbon dioxide. Now, that's more or less kind of just a coincidence, but it also is due to the fact that carbon dioxide is the biggest insulating factor in our atmosphere. So nitrogen, as most of our atmosphere, has very small insulation potential. So it's more on the paper cup side of things than the metal thermos, right? Oxygen, second most common element in the atmosphere. More like the paper cup than the metal insulating jug. Argon, third most common substance in the atmosphere. Fourth most common substance in the atmosphere, carbon dioxide. It, compared to the paper cup analogy, has this large thermal insulating capacity compared to those other gases. So consequently, it has a large impact. Changing carbon dioxide has a large impact on the insulation capacity of our atmosphere. And it so happens when you add all the other stuff that heat or cool it up, they kind of cancel each other out. Or very closely so. With me on that? So because of that, it's a nice convention in science to relate everything back to that carbon dioxide equivalent in terms of it's equivalent to change the insulating capacity of the atmosphere. It's not because our climate is just solely due to the carbon dioxide in the atmosphere. It's due to the cloud cover and hydrofluorocarbons in the atmosphere and the amount of volcanoes that go off on a yearly or average basis over long-term millennials. It's due to all those things, but when we mathematically add them up, it most closely matches the amount of carbon dioxide in the atmosphere. So we come up with an indicator and impact for all this different list of chemicals that's going to be related to carbon dioxide in the atmosphere, and we call it the carbon dioxide equivalence. Make sense? So it's a convention that we use to go from an emission amount, a massive emission, and move from that massive emissions to now a specific impact. Right? So we go from a technology, that technology may emit a wide range of chemicals. We can get the mass of those chemicals, and now we want to go from those emissions, we want to take those over into a particular impact. And that's what we try and do with this concept of carbon dioxide and global warming potentials. Okay. So if we can calculate the carbon dioxide equivalent for 40 kilograms of methane. So those 40 kilograms of methane might be the amount of methane that's leaked from a natural gas well over time. It might be a period of a year, it might be a period of 10 years. So we have some equivalent mass of CO2 is equal to the global warming potential of this compound, in this case methane, times the mass of that particular compound, that emission mass. So very simply, we have the 40 kilograms of methane, and there's a table in your text, 9.6. I'll show you that in just a minute. And this uses a 100-year time horizon, so we have to come up with a time horizon basically that You don't need to worry about this. This is just in the details of how we get this value of 25. Is it actually 25 or 8? That depends somewhat on this time horizon we use. So we come up with different values. But once we set this time horizon, then they're all comparable to one another. So the way we define this global warming potential is an equation in a system all in and of itself. So that's a process that we agree when we come up with this one particular impact, global warming impact. We're going to call that an impact. We're going to have a procedure that we go through to generate that. Think with me on that? And that procedure is then based on the chemical structures of that thing, the mass emitted, and the procedure. In this case is 100-year kind of residence time in the atmosphere. Very simple math, 20 times 40. We get 1,000 kilogram equivalents of carbon dioxide in the atmosphere. So you may have a lot of cows. Cows generate a lot of methane. If you've had me for 411, you may have heard me tell this story. They actually have, out in the University of Idaho, there was an EPA research project where they put methane monitors literally on the cow, follow them around to determine how much methane is generated from a cow, so you can calculate from beef production, how much does a cow methane generate, does a cow generate as it lives its life to go from calf to beef to your hamburger. Sorry if you're vegetarian, so I won't make anybody nauseous. So if you move from calf to hamburger, what's the carbon dioxide equivalent of that based on the methane emissions from the cow during its lifetime? People have actually done that study and measured that. Little known fact. You can talk about it at dinner with your roommates tonight, especially if you're having hamburgers, right? So we have different global warming parameters for different compounds. These are some of the very common ones over here. Chemical formula, approximate lifetime in the atmosphere, and then again, depending upon the base case we make, whether we look at a 20-year horizon, a 100-year horizon, or a 500-year horizon for those species in the atmosphere, we may have slightly different values that we come up with for that. And your textbook has these in a tabular format. So you could go into, again, if the question is what's the carbon footprint or the global warming potential for a hamburger at your local restaurant, rather than going to SEMA Pro, it might be quicker to go get that study on cows that I mentioned, calculate the methane that's emitted over the course of a lifetime going from farm to plate, and calculating CO2, the global warming potential, if that's the specific impact that you're concerned with. So, just real quickly then, the value of this is that we can do this. We have different species here, carbon dioxide, methane, and nitrogen oxides here. When we calculate their global warming potential, we can compare two different options, system A and system B, with different emissions amounts. So that's our emissions database. We can go to an impact factor here by multiplying those out. So in system A, we have a 454.6 kilograms of CO2 equivalent, or global warming potential. In system B, we have 590 kilograms of global warming potential. So now we can go to an impact, and we can make a decision between system A and system B based upon any impacts that we want to mitigate or reduce. So that's how we go from a technology to emissions to an impact category. And we're going to use those same types of tools in SEMA Pro and in the database, and we'll continue to talk about that on Friday. I took away a minute of your life. I will give it back to you in the future. Thank you for your time today. I appreciate that, and we will